evening. For those of you who don't know me, I'm Alan Morton, a very long-standing member of the Muswell Hill Sustainability Group and its community energy group, Energy. And I was delighted to meet Jean-Baptiste Fressoz last year at a meeting in Oxford, and that was to mark 200 years since the publication of Sadi Carnot's Motive Power of Heat, which was a groundbreaking work about steam power. And today, Jean-Baptiste joining us from Paris to bring us the story up to date, covering the last 200 years of energy supply and use. Jean-Baptiste is now at the Centre National de la Recherche Scientifique, and previously he worked at Imperial College London, which many of you will be familiar with. He has published recently in English More and More and More, an all-consuming history of energy, which I would urge you all to read. It's a wonderful book. And those of you who are lucky enough to be a member of the Muswell Hill Sustainability Group book group will have read this a few weeks ago, so we can highly recommend it to you. So, without any more ado, I'll hand you over to Jean-Baptiste in Paris. Thank you.
Well, thanks a lot, Alan. The book is a reflection from a historian about a very consensual notion, which is the idea of energy transition. What strikes me most is that this idea is perfectly normal, acceptable. The idea that, facing climate change, we have to do an energy transition, shifting entirely our energy system from fossil fuels to renewables in 3 or 4 decades. And why I was interested in this notion is that it's because history has played a discrete but very important role in justifying this future. When you pay attention to what politicians are saying, very often they refer to a kind of a phantasmatic history of energy. For instance, when they explain, like John Kerry recently, the energy transition is a new industrial revolution, as if there was anything similar between what we have to do and the previous industrial revolution. And you also find this very dubious historical understanding among experts, which is more problematic. If you take the last IPCC Group 3 reports, as you might know, in the IPCC, there are several groups. Group 1 is about climatology. Group 2 is about the impact of climate change, and Group 3 is about solutions, mitigation. If you take the last IPCC report, Group 3, its transition is all over the place. On a 2,000 pages PDF file, you will find more than 1,800 occurrences of the word transition. And interestingly enough, all the issues about sufficiency and degrowth are very secondary in all these reports. But more problematic is when they talk about history. You can find this phrase, energy transitions can occur faster than in the past, or a low carbon energy transition needs to occur faster than previous transitions, which is very, very strange indeed, because as you all know, for the moment, the previous energy transitions at a global scale are very mysterious. We have not passed the peak of any energy source. We are burning more and more coal, more and more oil, more and more gas, and also more and more wood. I talk quite a lot about wood in the book because wood is a very underestimated source of energy. For instance, right now, wood energy represents twice as much as nuclear energy on a global scale. And what I just said about energy is true of every raw materials. Basically during the 20th century, humanity has consumed a wider array of raw materials, and each raw material is consumed in greater quantity. And this is a very important point because very often we tend to confuse the dynamic of history of technology with the dynamics of history of raw materials and energy. And the two are very different. When we talk about technology, sometimes certain technologies do become obsolete. It is not the case with raw materials. under the impression of a complete technological transformation, raw materials keep expanding over time. I mean, one very, I think, striking example is the case of lighting and the use of oil for lighting. During the early 20th century, the main source of light in the countryside was oil lamp, kerosene lamps. And then, of course, came electricity. But nevertheless, today, just the headlights of the automobiles consume more oil than the world in the early 1900s, when most of the people were using oil lamps to produce light. So we've got an impression of a complete technological transformation, but raw materials are never obsolete. The only raw materials whose consumption has decreased in the 20th century is sheep wool, with the competition of synthetic fibers. And it's not necessarily a good news for the environment. So, I mean, when we are talking very lightly about innovation as a solution to our environmental problems, I mean, innovation might be important, but it is really contradictory with all the dynamics that happened in the 20th century, where we had plenty of innovations, and nevertheless, raw materials and energies have just kept growing and growing again. I mean, if people are talking about, and the experts of the IPCC Group 3 were talking about energy transition in the past, it is because it is true that history of energy has been written in a stagist way. When you take the most famous books on the history of energy, most of the time they have a very similar structure. They're going to talk about wood and hydraulic energy in pre-industrial times. Then they will talk about coal and the steam engine in the 19th century, and they will deal with oil and internal combustion engine in the 20th century. The problem with this story is that it tends to, I mean, it makes sense if you look at energy in relative terms, in terms of shares. If you do that, you can see this kind of graph. You know, it seems to be describing an energy transition from organic energies to coal energy occurring in the 19th century. But in fact, when you look in absolute values, all the traditional energies do grow during the Industrial Revolution, during the 19th century. There is more and more hydraulic power in most industrial countries. In Britain, hydraulic power increased in the 19th century. In France, it's multiplied by 3, despite the steam engine, right? Wind power also increased a lot, simply because of navigation, of course, and also because of stationary wind power, which in the US and more generally in America, but also in Europe, was a very, very important source of energy for agriculture. In the late 19th century, you had several millions of windmills pumping water in the Midwest, in the US. And this technology had a very tremendous historical importance because it allowed the irrigation, also to give water to the animals. So it's really a very key technology in the opening of the Midwest and the transformation of the market of agricultural goods on the world scale. In the same way, during the 19th and in the 20th century, the human muscular energy is growing. You got more humans, they are better fed, and they are using more efficient tools. So, of course, the input of human energy is growing and keep growing today. The other reason why historians have written about transition in the past, first is because they have looked at energy in relative shares, in relative terms, in terms of shares, in terms of percentage. And it's also because they have taken for granted the statistics given by the state. I just give you an example. This is a very famous graph in history of energy. It's taken from an important book by Anthony Wrigley, Energy and the Industrial Revolution, and it seems to depict an energy transition. Indeed, firewood disappears in Britain, and in the mid-19th century, it is true that very few British people would burn wood to heat their houses, and steel making had already entirely shifted to coke, metallurgical coke from coal, of course. But in fact, wood still played an extremely important role in the British energy system because it was indispensable to extract coal. Pit props in the early 20th century in Britain consumed 4.5 million cubic meters of pit props in the early 20th century. It is more than the amount of food that was burnt in Britain in the 18th century. So just to produce energy, Britain used more wood in the 20th century than it did in the 18th century. And it is even worse because pit props, of course, it is construction timber, and you need a far larger area to grow construction wood than to grow firewood because you need to wait for the trees to grow. The result is that Britain is importing most of its wood in the 20th century, and one third of the wood that it imported was for the mines, for the coal mines. I mean, this is a picture from Cardiff Harbour in the 1930s. It was just the pit props for the mines of the whales. So it's really a very large amount of timber. I mean, and it is true for all major industrial countries in the 20th century. I mean, the the amount of mining timber increased until the 1960s, when there is a modernization of coal mines in the rich world. I mean, the case of the USSR in the 1960s is very striking. They use an enormous amount of mining timber. It is timber from Russia, which is used in the mines of Ukraine. So it is really this kind of very important interaction of different spaces that allows the production of coal. Coal is not a national resource. I mean, Britain was completely dependent on international trade, intra-European trade, for its provisioning of pit props. And it was a key topic during the two world wars, actually. So when you talk about coal, you need to talk about timber. I mean, without timber, without abundant timber, Europe would have had no coal, or hardly any coal, hardly any steam, no steel, no railroad, etc., etc. So coal and wood are not in competition. I mean, it's really a key thing. Normally, you talk about that in terms of transition and competition and shift from wood to coal, but in fact, coal and wood are in symbiosis. I mean, you need more and more wood and timber in the 19th and in the 20th century because of coal. In the same way, the idea that there is a kind of transition from coal to oil in the 20th century does not work at all. For one simple reason, I mean, to make a car, you need a lot of coal. Ford company would need around 7 tons of coal to produce a car in the 1930s. There are calculations made for Britain that show that in the interwar period, for each ton of oil that was burned in Britain, 2.5 tons of coal were required to produce all the steel to make all the infrastructure for the oil, the cars, the pipelines, the tankers, the storage, etc., etc. And of course, once you got oil, you got trucks and dump trucks in particular, and that decreased the cost of coal. I mean, coal becomes much cheaper and you can access to coal almost everywhere where there is a road, whereas before the dump truck, coal was expensive because of its distribution. I mean, it's of course difficult to transport and to sell. In the same way, because of motor trucks, wood energy has increased a lot in the 20th century. I mean, one of the big transformations of the energy system in the poor world since the 1960s is the expansion of charcoal. Charcoal is an urban technology. It is difficult to transport wood, but it's easier to transport charcoal. And like very large cities of sub-Saharan Africa, like Lagos, Kinshasa, Dar es Salaam, they burn over 2 million tons of charcoal a year. Paris in the 1860s, which was probably the city which was burning the most charcoal in the world at that time, is burning only 100,000 tons of charcoal a year. Actually, a large city like Kinshasa burns probably more firewood than France or Germany in the late 19th century. Interestingly enough, you also have a very big expansion of wood energy in the rich world. I mean, if you look at statistics about renewable energy, wood energy remained the first renewable energy in the rich world. I mean, it is mainly in the industry, in the production side, that you consume wood energy for the, especially for the production of paper, of cardboard. So here you got a symbiosis, which is at a, I mean, at a distance. Basically, you've got an economy which is growing thanks to fossil fuels. So you got more goods to package, so you need more cardboard. And the paper industry is a very big consumer of wood energy. And is a very big consumer of energy. I mean, the paper industry is the fourth industrial consumer of energy. The first being steel, second is cement, third is the chemical industries in general, and fourth is the paper industry. I mean, one very good example of this I mean, of no transition, of non-transition is probably the case of the Drax power plant in Britain. I guess you have all heard of it, so I'm not going to expand too much. But when you look at the figures, it's quite amazing. This, I mean, just one power plant in Britain near Leeds do consume right now 12 million tons of wood per year. This is 3 to 4 times more than what Britain burned in the 18th century, just to produce 1.5% of British energy. So after 2 centuries of energy transition, we reached this great result that Britain actually burns at least 3 times more wood than it did in the 18th century. So, I mean, in the second part of the book, I try to explain, I mean, the emergence and the success of this idea of energy transition. I mean, when you tell the history of energy like this, studying the symbiosis and the expansion of all the energies, of course, it is not the idea of transition which comes to mind. But actually, energy transition is a very recent notion. I mean, for most of the 20th century, experts would not talk about energy transition at all. They would rather see the future of energy just as a bigger present. This is a futurology exercise made by a promoter of solar energy in the US in the 1970s. As you can see, according to him, everything is going to increase. Solar, but also nuclear, but also coal, etc., etc. The future of energy is not very different from the present. It's not a complete shift in the energy system. The idea of energy transition comes from a very narrow set of experts. They are atomic scientists, and they are also neo-Malthusians, people that are very concerned about the growing scarcity of resources given the growing population. The word energy transition is invented, I mean, to my knowledge, by this person, Harrison Brown, who is an atomic scientist from the US working for the Manhattan Project. And energy transition, actually, at the beginning, it was the shift of an electron around its nucleus. It was a term of physics, of atomic physics. And then it was used by atomic scientists to talk about the future of energy. And it was mixed to another key word of the time, which was, of course, the demographic transition. You know? So this idea of energy transitions comes from a kind of utopia of a nuclear age that would be provided with the breeder reactor. So the technology that these people were promoting was not the fission reactor as we know it, but the breeder reactor, which allows you to have access to an enormous quantity of energy. And it's only like this that the nuclear energy can have a kind of civilizational role, that it can expand time horizon over millennia of energy. The idea of energy transition is very clear in this graph, which is a very famous graph produced by the theoretician of peak oil, Marion King Hubbert. I mean, all fossil fuels energy form a narrow peak because you look at history of humanity over a 10,000 year time frame. And all fossil fuels make a peak because you contrast that with the amount of energy you can access with the breeder reactor and with nuclear energy. So basically, I mean, really what I want to emphasize is that at the beginning, The idea of energy transition comes from this milieu, and the energy transition, according to these people, will be coming in a faraway future. At a global scale, they know that there is a lot of coal, a lot of oil, and that the energy transition, the end of fossil fuels, if you look at the lower graph, you can see that it will, I mean, the end of fossil fuel is is in the midterm between now and 1,000 years. So it's the 23rd or 24th century that we will have finished the energy transition to the atomic age, right? So the thing that really puzzled me was that how come that it is this futurology, which is very strange, very heterodoxical. Why is it this futurology of the energy transition which was used to reflect on the climate change? And the reason is really because it is at the same time that you got the energy crisis in the 1970s, and that climate change became something on the political agenda in the US at the end of the 1970s. I mean, the first politician to talk about an energy transition was Jimmy Carter. Interestingly enough, he does that basing on a false history. He looks at history of energy in relative shares, and he comments this graph on TV saying that in the past, the US have done two energy transition, one from wood to coal, the second from coal to oil, and now we've got to do a third energy transition. It is a very original representation of energy. Normally, you look at the energy dynamics with this kind of graph at that time, and it's certainly not the idea of energy transition that comes to your mind. In the 1970s, there are all sorts of reflection where you look at energy in relative shares and you start to talk about energy transition or waves of transformation of the energy system. This idea of energy transition is then taken up by economists. And why energy transition was applied to the climate issue, there is a very simple reason. It's because the first economists to deal with climate change were energy economists who had worked on the energy crisis. It is very clear for the case of the Nobel Prize in Economics, William Nordhaus, who got his Nobel Prize for his work on climate. In 1973, he published a paper explaining that, okay, oil is getting more expensive. Does it mean that we have to conserve oil, restrict our consumption? Not at all. On the contrary, we need to get the oil now while it is very valuable, because in the future, because of technological progress, it might be worthless. And even it will become worthless because of the breeder reactor, which will make oil obsolete. 2 years later, he writes the very first academic paper by an economist on climate change, and he has exactly the same reasoning. There is an issue with greenhouse effect. Does it mean that we have to reduce our emissions? Certainly not. It will be much easier to do the transition later when we'll have the breeder reactor with the proper technologies in the future. So energy transition was really a delaying tactics. And it was used very early on by the oil industry. I mean, as soon as 1982, Exxon industry in the US was explaining that, of course, there is climate change. They were not climate skeptics at the time. But the interesting question is, will the energy transition happen before than the climate catastrophe? And it was a very astute way of presenting the problem at that time, because most of the climatologists would say that, the climate change catastrophe would come in the second part of the 21st century. So it was clear for everyone that by then we would have done an energy transition. And this idea of energy transition and the idea that in the past there had been energy transition kind of, it was a very reassuring futurology. And the energy transition had a lot of success in the international expertise among the IPCC Group 3 and in the international negotiation. And it is quite easy to see the strategic nature of the discourse. I mean, Robert Weinstein was the first head of the IPCC Group 3 panel. He was also the chief negotiator for the US for the Conference of Rio in 1992. And in the archive, you can see that he received his orders from John Sununu, who is George Bush's chief of staff. And John Sununu very explicitly told him, okay, we're not going to fix emission targets. we are not going to accept that the US energy consumption will be kind of restricted by an international agreement. We're not going to compensate for the climate damages. So no money, no target, play the technology card. And it makes perfect sense for the US negotiator to put forward their capacity to innovate to solve the issue. I mean, right, very little time after this discussion took place, George Bush father made a talk about the White House effect. You know, there was the greenhouse effect and there was the White House effect, which was promoting innovation to solve the climate issue. And it is true that this idea of playing the technology card, it is precisely what the experts of the IPCC Group 3 have been doing for over 30 years. When you look at their report, I mean, it's a very rough method. I just counted the number of occurrences of different words. And basically, it's very technological. All the discussions are about new technologies. Innovation is omnipresent in the discourse. Sometimes they are very dubious innovation. For instance, in the last report of 2022, there is a series of paragraphs on the Hyperloop, a kind of very futuristic train that will be developed in the future by Elon Musk. There is so much on hydrogen and even hydrogen airplanes. So it's really geared toward new tech and innovation. And the issues of sufficiency and degrowth are almost inexistent. I mean, it's only in 2022 that you've got some treatment of the question of sufficiency. The result of that is that at a global scale, I mean, no transition is coming. You look at the expertise of the International Energy Agency or the American equivalent. I mean, nobody is saying that, yeah, we will, I mean, there is a probability of getting out of fossil fuels in due time. I mean, it won't happen. And it's very easy to understand because, you know, energy transition is a very strange notion. It's not a very serious notion. It's a slogan. It's not a scientific notion. And it has, I think, created a lot of confusion, a lot of scientific confusion, and a lot of political delaying tactics. I will stop here. I hope it was all clear. And thank you for your attention.
Thank you very much. That was a wonderful talk and I think a very challenging set of ideas for us. So we've now got some time for questions. So a roving microphone is about to miraculously appear. So I'm sure you've got lots of ideas and thoughts about what Jean-Baptiste has been saying. Jenny in the front row. The microphone, please.
Can you hear me?
Yes.
Jean-Baptiste.
Yeah.
Given what you've said, if you were in charge of organising a climate policy for a country or even for the world, what would you recommend one did, given all the problems with transition that you've outlined? Yeah.
It's not a position I would fancy having because I think it's extraordinarily difficult. And it would be, I think it would be doomed for failure, basically. But what I would recommend is probably, accepting that there will be CO2 in the economy, in the world economy in 2050, because there are a lot of sectors that are going to be extremely difficult to decarbonize. Putting a lot of energy where it is possible, like electricity production, where you've got, some, powerful solutions. Even if they are not perfect, you can do a lot of things on electricity production. And then I think for all the other sectors, the key issue is about, redistribution. It's about limiting consumption, reducing consumption of cement, of steel, of meat, of plastic, etc., etc. And if you cap this kind of consumption at a global level, of course, the key thing is about redistribution. And I think the problem with the idea of energy transition, it allows you to imagine an economy growing after 2050 without having any impact on the climate, which is deeply wrong. That won't happen. And because of that, all the issues of redistribution become secondary. I mean, look at the IPCC report. It is quite, I mean, for instance, they work under what economists called Pareto optimality, which means that you cannot reduce the well-being of one or the GDP of one nation, basically. So I mean, all these issues, which of course are crucial. I mean, the size of the economy of wealthy countries should be on the table. All these issues have not been discussed. So, I mean, I think just, acknowledging that technology won't be able to do everything that we want to do is probably the first step to have a different kind of discussion, a much more democratic too. I mean, because if we are talking about redistribution and limiting certain consumption, it has to be decided in a democratic way. I mean, to be accepted in any case.
I think for me, the most depressing thing is that in this country, we've decarbonised our electricity to a certain extent, but that's just enabled us to use more energy. So it hasn't really made a difference. But the question I wanted to ask you was, do you think France then was very canny to move over to nuclear power? And should we all be doing the same thing?
No, I don't think it was. I mean, in France, all the issue is about nuclear energy or renewable energy. And I think nuclear energy is, it cannot be globalized. It's very expensive, very cumbersome. It costs dozens of billions of pounds to make a nuclear plant in Britain or in France. It takes 20 years. They run overcost, overtime, all the time. And there are very few companies that can build nuclear plants, 5 of them globally. And in many countries, you don't really want nuclear power plants because there are also the problem of residues and nuclear weapons. So, no, I think it's certainly not. I mean, it can help in the case of France, because there is nuclear plants now. It's difficult to say we're going to shift to renewables or something like that. It's complicated, and of course there's so much investment and people working in this sector that it's difficult to move away from that. But globally, it's certainly not the technology that is expanding fast. I mean, what is expanding quickly for the production of electricity is renewables, solar panels in China in particular. But then you have to recognize also that there will be backup for solar panels. I mean, the case of China is quite clear. I mean, you got a huge expansion of solar panels and wind turbines, especially in the western part of China. But electricity is sold on the eastern part of China, where the population is basically. So you need to transport the electricity over 2,000 miles, and that costs a lot. I mean, what is expensive is the grid, basically, not so much the solar panels. And to recoup on the investment for the grids, I mean, they also build up coal power plants next to the solar panel. It makes perfect sense. So, I mean, yeah, even electricity, which is the easiest part of the transition, is not that easy. I mean, you have to recognize that it is not that easy. And electricity is the first and easiest part, because when you start talking about the production of materials, concrete, steel, plastic, etc., everything is more industrial heat. I'm not talking about aviation, of course, which more or less impossible to decarbonize. I mean, we have very strong technological bottleneck. We have to recognize that. And we have to have a policy of reduction, basically, if we want to have any chance of really having a strong impact on emissions.
Yes, thanks very much for that talk. I must say, when I read more and more and more, it was a revelation to me, because it never occurred to me that there was no transition, and in fact everything was going to be used more than it had been in the past. And it was new to me, that, and I'm just wondering to what extent your views are recognised and supported by other people around the world, or whether you're a lone voice.
No, I mean, basically, the idea that, the fact that at a global scale, energies have piled up on each other is trivial, because you can see that on any graph showing the world consumption of energy. And you see very quickly that, coal keeps expanding, oil has added on top of coal. And what is a bit more original is the fact that energies and material are so intertwined and codependent. And the fact that, for instance, that coal necessitated so much wood to be produced, or that to extract oil you need so much steel and therefore so much coal. So it is more like the symbiosis argument, which is slightly a bit newer than but the fact that energies are adding up at a global scale is very well known. There is one important historian called Vaclav Smil from Canada. Interestingly, he has an engineering background, so he asks different questions from a standard historian, I would say, much more materialist, much more rigorous on the technologies. He's a very influential voice who says that it's going to be very difficult to decarbonize the world economy by 2050. Don't dream. I mean, because he put the emphasis on what he calls the 5 pillars of industrial world: cement, steel, plastic, fertilizers, all these materials that are going to be very difficult to decarbonize. But strangely enough, when he talks about the past, he keeps talking about energy transition because he looks at the relative shares. So he has a very standard view of the past, but a very realistic view of the present, I think. So no, of course, I'm not alone. I mean, it's and in fact, it's the energy transition which is radically strange and heterodoxical and and conventional. What I'm saying is perfectly conventional, in fact.
So, right, so, go on. No, you want to ask you? Okay, thank you. Jean-Baptiste, I don't think you've mentioned the development or potential development in nuclear fusion and where that might sit on the energy curves of the future. Everyone's obviously talking about nuclear fission there, but if I've got it the right way around, I can never remember. But do you see any prospect of that coming to our rescue?
No, I mean, honestly, it will be very high tech, very expensive, and it is mainly limited to electricity, and electricity is just 40% of emissions. I mean, we keep talking about electricity, but all the time we're talking about electricity, but we have to remember that electricity is just 40% of CO2 emissions. I mean, so we have to do something about these 40%, of course, but then there is all the rest, and fusion it would be mainly useful for the 40%, and then it will be the 40% in the rich world. So no, I don't think it is. I mean, it is this kind of faraway future technology that prevents us from doing simple things now. I mean, that's really what worries me most. I mean, the other very futuristic thing, not so futuristic as fusion, is hydrogen. The idea that we're going to do the thing that we do with fossil fuels, but with hydrogen. And because hydrogen can be produced with renewable energy, it will be green hydrogen. The problem with that is that you need really a lot of electricity to produce hydrogen at scale. For instance, I made some calculation that I present at the end of the book. I mean, one of the difficult sector to decarbonize is steel, because coke is used as a reductant to take the oxygen atom, which is linked to the iron atom, right? I mean, for that you could use hydrogen, but to produce the hydrogen that could replace the coal used to produce the 1.7 billion tons of steel. I mean, the problem is the scale. You would need more electricity than the production of the US, for instance. So we are talking about really serious amount of electricity. It is the same thing for the hydrogen for aviation. I mean, you would need a tremendous amount of electricity just for Roissy-Charles de Gaulle Airport. I mean, these calculations were made by colleagues working actually in the aviation industry. They showed that you would need like 10 nuclear plants to produce the hydrogen, just to produce the kerosene for the planes taking off from Charles de Gaulle, from the Paris airport. So, I mean, the things do not add up, basically. And then the problem is that hydrogen is very cumbersome to store. It's liquefied hydrogen. It has to be stored at minus 250 degrees Celsius, so close to the absolute zero, basically, which is very tricky. And then even like that, a liquid hydrogen is much less energy dense than kerosene. So you would need larger tanks for everything. And for airplanes, it's a disaster, basically. I mean, it just doesn't work at all. So, yeah, I mean, And then, I mean, there is no demand for hydrogen in the industry. People do prefer to use gas, which is much easier and with all the equipment. I mean, what is interesting is since writing the book and after the book, I had discussion with people working in these sectors. And when you talk to engineers that are really working hands-on on the technologies, they keep talking about the difficulties. For instance, all the compressors have to be changed when you are dealing with hydrogen because it's a very small molecule and that escapes very easily. Everything has to be changed. So it is this kind of high-tech solutions which are not coming. I mean, we have been talking about hydrogen society, hydrogen economy from the 1960s now. I mean, it's a very old promise and it has not advanced. In the book, I put the picture of an aviation airplane from 1976, and they have gone nowhere since then. And the other promise is carbon capture and storage. I'm not going to talk, I guess you have heard a lot about it because the British government has announced enormous investment in carbon capture and storage recently, but it's a very, very problematic and dubious technology. I mean, I've, not in the book, but in another paper, I have traced the history of the carbon capture and storage promise. I mean, nobody believed in the carbon capture storage in the 70s, 80s, 90s, early 2000s. And then it became it was promoted by the IPCC Group 3, once again, by a very special report that was mainly based on industrial expertise from the fossil fuel and the cement plants and so on and so forth. So it's these kind of technological promises that won't work very well, basically.
Could I ask about the recent projections in the United States that they'll be using more and more electricity, both for manufacturing or digital coinage, but also AI.
Yeah.
And the big tech companies are then trying to buy up their own energy supplies, including reopening 3 Mile Island, which is quite a remarkable comeback.
Yeah.
But what I wondered is what effect will this have on energy in the United States generally? Because what you'll see is these big tech companies safeguarding their own assets and probably building new plant next to their factories or their server farms, so they'll have low transmission costs. And this will mean that for the rest of the population, the transmission costs will be higher, they'll have less access to renewable energy and so on, and you'll probably end up with different prices for different consumers, or even more exacerbated than today. Have you any comments on
I'm not an
what's
expert,
happening?
but I've read papers on the New York Times, basically, so nothing very expertise. But basically, they show that right now, data centers, not only AI, but data centers in general, do have impact on the electricity bills of populations. When you've got a new data center, it creates problems basically already. And the expansion that is forecasted for AI is striking. We are talking about tripling of the electricity consumption of data centers in the next couple of years. We are talking about 2030. It's really an amazing curve that was recently presented by the American Energy Administration. On the other hand, at a global level, if you read the last report, the 2024 report of the International Energy Agency, they show that, for instance, air conditioning is even a bigger issue because it's everywhere, because the tropical world is getting richer. With economic development, they are installing more and more air conditioning units. And in the northern latitude as well, we are installing. In Paris, people are starting to install air conditioning, which was not the case a few years ago. And that would be a big draw on the electricity on the grids, bigger than the AI. Okay, so AI is of course very impressive, but we tend to focus on the high tech, the new, the innovation. And here I want to refer to a book by my former colleague David Edgerton, The Shock of the Old, who showed that historians and also the public discussion tends to be obsessed with the new, but we have to look at the old and how the old expands, and air conditioning is probably part of the thing that are going to expand a lot because of climate change, basically.
Well, I'd just like to... Oh, Jenny, do you...
Yeah, what's your next project?
Now, I briefly mentioned the case of the human muscle and the muscle in general. And I wanted to write a chapter on the human muscle because very often history of energy tends to be obsessed with machines and they don't talk so much about the human body. And I wanted to integrate the human muscle in the history of energy, which I think would be, I mean, it would allow you to see different things. So this is the next project. And actually, there is a lot of data that shows that, of course, the human muscle is getting more and more used in the 20th century. I mean, you've got more people, small agriculture expanded in the 20th century. A recent statistic that struck me, the size at a global scale, the average size of farms has decreased since 1950. And we've got a vision from the rich world where of course it is the contrary that has happened. I mean, farms have expanded, but there is so much, the demographic increase in the poor world makes that the size of farms has decreased. For instance, there is more miners, artisanal miners now than any time in history because of the price of gold, basically. Just the fact that gold has become so expensive after 2008 made that you've got like 15 million people around the Sahel in Africa that are digging for gold with very rudimentary tools, with shovels, picks, wheelbarrow. So, I mean, I like to really talk about that. I mean, the modernity of the human muscle. And then the human muscle is is using more efficient tools, but not necessarily motorized. So, I mean, it's, the story of technology that are not regarded as important, but like the shovel, for the spade, for instance, but which plays a crucial role in the 20th century.
Very much, Jean-Baptiste. That's a very interesting talk. You've really changed, I think, and reoriented a lot of our thinking about growth and innovation. And in Britain today, the government talks a lot about growth and innovation, and I think you've undermined that kind of rhetoric as being rather a set of false gods. Mm. And so I think, we've got a lot of thinking to do, and I want to leave with the words that actually are a quote from you, that at the very end of your book, you said, thanks to transition, we are talking about trajectories to 2010, electric cars and hydrogen-powered aircraft, rather than material consumption levels and distribution. Very complex solutions in the future make it impossible to do simple things now. So we've got to take your work to heart and go out and do good things. So thank you again.
Thank you very much for your interest. Thank you for the invitation. Goodbye. Goodbye.
Bye. Oof.